Hello, everyone. I'm Wang, a postdoc working at FCEV Energy Research Center. Today, I will give a presentation about the integration of renewable hydrogen production, compression, and storage for vehicular and stationary fuel cells. Here is the outline. In this work, an integrated hydrogen system is developed for transportation and grid operations. It mainly includes a transportation system fueled by 100% renewables and a hydrogen fuel cell system for stationary power application. First is the background. As we can see from the left-hand side figure, with the increasing penetration of renewable into the grid, a dark curve exists. It means the conventional power plants are being forced to ramp their load more rapidly and aggressively during a daily operation. When the PV penetration reaches 45%, there is a 50 gigawatts variation in the morning and a 35 gigawatts variation in the afternoon. The right-hand side figure is the OUC PV output profile for a shorter period of time on a cloudy day. It shows a 6 megawatts variation in 1 minute. Currently, Florida's installed solar capacity is less than 5% of its load, but it's expected to reach 25% by 2030. The increase in the PV penetration will lead to more challenges for the power plant operation. One solution to mitigate the steep ramp operation is adding the energy storage system. For example, hydrogen can be produced at utility scales as a controllable load to provide both long and short duration storage capacity. As we know, hydrogen is a clean and flexible energy carrier. It can be produced from diverse renewable energy sources such as wind and solar, and used in a broad range of applications. In this work, transportation and power generation are mainly discussed. The power generation can either use fuel cell, or blend hydrogen with natural gas and feed to the existing gas-fired power plant. Clearly, hydrogen system can improve the grid flexibility and resilience. In this work, an integrated system for green hydrogen production, storage, and flexible utilization is developed. Since hydrogen production from the renewable electrolysis is a controllable load, it can reduce the grid fluctuation and improve the resilience of the energy system. My colleague Peter is working on PV smoothing using hydrogen electrolyzer, and she will also give a presentation in this session. On the other hand, the generated green hydrogen can be used for fuel cell electric vehicle refueling and fuel cell stationary power applications, such as EV truck charging or serving as a backup power source, etc. In addition, hydrogen can be blended with natural gas and used to fuel the existing gas-fired power plant. Since the varied renewable supply and hydrogen consumption demand are mismatched in most cases, a large separator vessel is required to store green hydrogen for different transportation and grid operations. The feasibility and flexibility of the integrated hydrogen system provide a transition to net zero emissions. Now, I'd like to talk about the transportation system. It includes a modular system of cascade hydrogen storage for fuel cell truck refilling and a hydrogen stationary fuel cell system for EV charging. Currently, most of the heavy-duty fuel cell trucks are designed with hydrogen storage pressure of 350 bars. Therefore, multiple stages compression and a cascade storage tanks are required in a hydrogen refilling station. Due to the pressure constraints of the storage tank, single modular system has service gap to refuel the truck. We found that 4 modules enable to refuel truck in a row for a whole day. In this work, about 5,000 kilograms of green hydrogen is used to refuel 144 trucks in a day. Stationary fuel cell can operate at low pressure and no compression is required. When the same amount of the green hydrogen is used by the stationary fuel cell, 146 electric truck with the same range as the hydrogen fuel cell truck can be charged. In addition, the charging time depends on the power of the charger. 13 supercharger with 350 kilowatts power capacities are used to charge all the electric trucks in a day. A spherical storage vessel can store large amounts of hydrogen for the daily transportation operation, and it can guarantee that the heavy-duty trucks are fueled by 100% renewables. On the other hand, solar energy is varied for different regions and seasons. As we can see, there is a big difference of hydrogen production on winter sunny day and summer sunny day. More details will be discussed on the next slide. Based on the left-hand side solar GHI map, we found that Central Florida's annual PV capacity factor is about 29%. If all the solar energy from a typical 75 megawatts PV field is consumed by a 45 megawatts electrolyzer, the capacity factor of electrolyzer is 48%, which is acceptable. It should be noticed that on the winter sunny day, all the solar energy can be used by electrolyzer. But on the summer sunny days, since the electrolyzer only has 60% of the PV capacity, the upper region of the solar energy will be sent to the grid. Only 75% of the solar energy is used for hydrogen production. As we can see, the hydrogen produced on summer sunny day is more than the storage vessel hold up. Therefore, the excess hydrogen will be sent to the gas-fired power plant. The details of a typical hydrogen heavy-duty truck are listed in the top right table. Once the pressure is doubled from 175 bar to 350 bar, the amount of the hydrogen in the vehicle vessel only increased about 80%. Clearly, hydrogen is not ideal gas, and it shows the nonlinear nature of density. In this work, a cascade tank configuration is adopted for truck refilling. The minimum operating pressure of tank 1 is 185 bar, and it can charge the truck from 20 bar to 175 bar. The tank 2 is the high pressure one. The minimum pressure is 360 bar, so it can charge the truck up to 350 bar. To capture the transient performance of refilling station, a dynamic model of hydrogen storage tank is developed. Besides the mass balance and energy balance, the non-ideal gas property and the heat transfer with the surrounding are also considered. Then, cascade tank is compared with the single tank configuration. Even though both configurations have the same amount of the total volume, usable hydrogen is in a single tank is less due to a higher operating pressure. Correspondingly, high pressure tank requires a more frequent recharge, and cascade tank 2 has a shorter time to refuel compared to the single tank. In this work, both heat exchanger duty and the compression power consumption for the storage tank recharge are calculated. We found that cascade tank configuration leads to more than 4% energy saving. The dynamic performance of storage tank for truck refilling is shown here. We can see that in 1 hour, a single cascade modules can charge 3 trucks in a row and refuel tank 2 back to the full load. After 4-hour truck refillings, additional 4 hours are required to refuel tank 1. Each 8-hour is a complete cycle, and a single modular system has a service gap to refuel the truck. When 4 modules are used, there's no any gaps in the cycle. If your truck refilling lasts for a whole day, 144 trucks can be charged using green hydrogen. One important application of stationary fuel cell is generating renewable power to charge the EV truck. The electrical truck has the same range as the hydrogen fuel cell truck, but its charging time depends on the charger power capacity. 1.9 hours of charging time is required with a maximum charging power of 350 kilowatts, which is much longer than a hydrogen truck refilling time. As I mentioned before, 146 electric trucks can be charged using green electricity, but 13 superchargers are required to charge all the trucks in a day. If 30 minutes EV charging is desired, a 1.3 megawatt supercharger is required, which is not available today. In addition, hydrogen refilling economy of fuel cell truck is expected to keep increasing. That also makes a fuel cell truck more competitive in the future. Honda company is manufacturing a new generation of fuel cell truck with a hydrogen storage pressure of 700 bar. The higher pressure leads to more usable hydrogen and a longer range per filling. The range of the new truck can reach the 500 miles, and the filling time is still 10 minutes compared to 3.8 hours charging time of electric truck. Once the vehicle tank pressure increases from the 350 bar to 700 bars, 3 tank cascade storage tanks are used in refilling stations. Also, pre-cooling is required. The tank size and operating pressure should be optimized to minimize the energy consumption of refilling. Besides charging EV trucks, hydrogen stationary fuel cells can also serve as backup power or peak power, the peaker plant. As we know, the grid demand is fluctuating. Besides the base load and load following plants, peaker plants are used to meet the peak demand. From the right-hand side figure, we found that a gas peaker plant has a very low capacity factor, and its cost is much higher than solar PV. Solar plus energy storage system can be used to replace a conventional peaker plant and reduce the cost. We found that solar plus battery system has been implemented, and it's more suitable for small and short duration peak demand. Hydrogen system can provide long duration and large scale storage with a lower marginal cost than battery system. Therefore, solar plus hydrogen system can be implemented for large or long duration peak demand. A dynamic model of stationary fuel cell system is developed using JFrog software. It includes a fuel cell stack, air compression, hydrogen recycling, and thermal management. A higher plant efficiency is obtained using fuel cell than gas peaker plants. It should be noted that hydrogen stationary fuel cell is not limited to pan fuel cell. Based on the operating temperature and the stack load capacity, alkalis, solid oxide, and other fuel cell even use blend hydrogen and natural gas as fuel can also be considered. To conclude, integrate a system for green hydrogen production, storage, and flexible grid and transportation operation has been developed. 100% renewables refilling of fuel cell truck and electric truck has been implemented. Hydrogen fuel cell truck refilling stations with cascade storage tank has been developed, and 4 modules of refueling systems enable to charge fuel cell truck in a row for a whole day. Hydrogen fuel cell truck has much faster refilling time compared to electric trucks for the same range. Solar hydrogen system can replace gas peaker plants and reduce the utility peak demand cost. Recently, we are working on electrochemical hydrogen compression. Compared to conventional mechanical compression, it shows a higher efficiency. In addition, it can be integrated with electrolyzer for process intensification. Since the GPROM software provides the powerful tools for the uncertain analysis and optimization, other works related with the uncertain quantification and dynamic optimization can be conducted. Finally, I'd like to acknowledge DOE for funding our research and thank you for your attention. I'm glad to answer any questions online. Also, please feel free to contact us through the email.